In this video, we'll analyze RC circuits. Specifically, we'll look at the current through the circuit and the charge on the capacitor as a function of time. And so to do this analysis, we'll want to recall Kirchoff's laws. More importantly, we'll want to focus on law number 2, namely the loop rule, that if we go in a closed loop in a circuit, the total change in potential will be 0. With that in mind, let's draw out our circuit. So we're going to consider a circuit with a battery, a resistor, and a capacitor. Let's label these. This will have electric potential epsilon. This will have resistance R, and this one will have capacitance C. And so we're going to analyze this quickly with Kirchoff's law. We have this unknown current I, which might be a function of time, and we have an unknown charge Q, which might also be a function of time. With that, I'm going to loop clockwise, which means I'm starting by crossing the battery from the negative terminal to the positive terminal, which gives me an increase in electric potential of epsilon. I then cross the resistor in the direction of current, which means we lose electric potential minus IR. And then lastly, if we think about it, the current, since it's conventional current, is depositing protons on the top plate, leaving negative charge on the bottom plate. And so we have our potential across the capacitor, which will be minus Q over C. Recall that I am getting this by using the definition of capacitance, C equals Q over V. Therefore, V is equal to Q over C. And so at that point, we return to our starting position, and so we can go ahead and set this equal to 0. Now let's pay attention to this equation. Again, I and Q might be functions of time. So let's consider what happens at t equals 0. Let's suppose that we started off with an uncharged capacitor. In that case, we can say Q equals 0, and therefore epsilon minus IR equals 0, which gives us our usual current for a battery resistor circuit. I is equal to epsilon over R. So this is case 1, the short-term limit. Next, we can consider case 2. T goes to infinity. And as t goes to infinity, we can imagine that our current is depositing more and more charge on our capacitor. And so as Q increases, I decreases. Thinking through it, that means that eventually we reach a state in which I reaches 0. We'll prove this quite shortly. But as t goes to infinity, I goes to 0. And therefore, we are left with epsilon minus Q over C equals 0. And we can figure out the final charge on our capacitor. Q is equal to C epsilon. So now that we've considered the limiting cases, let's go ahead and see how this behaves over time. So the crucial step here is to think about how I and Q are related. And in particular, I, I'm going to argue, is equal to dQ by dt. I is a positive quantity that describes the flow rate of charge through our wire. But all of that charge is being deposited directly onto the capacitor, and therefore the rate at which the capacitor's charge is increasing is exactly equal to I. It's important to note that in the case of a discharging capacitor, I discharge is actually going to be equal to negative dQ by dt. And we'll hopefully elaborate on that in a later video. But in this case, since we're charging, I is directly equal to dQ by dt, leaving us with epsilon minus R dQ by dt minus Q over C is equal to 0. And you might recognize this as a separable differential equation. So let's go through actually solving this. Our goal is to isolate our variables. So I'm going to begin by isolating dQ by dt. So R dQ by dt is equal to epsilon minus Q over C. I've simply added Q over C, or added R dQ by dt to both sides. I'll then divide by R. So epsilon over R minus Q over RC. At this point, we're pretty close to being able to separate variables. We'll multiply by dq on both sides. Got epsilon minus q over rc, all multiplying dt. And so now I'm just going to go ahead and combine terms. So this is equal to c epsilon minus q all over rc. And to complete our separation of variables, we note that this is our term, which is dependent on q, so it better come over to the dq side. So we'll get dq over c epsilon minus q is equal to 1 over rc dt. And so at this point, our variables are separated and we can go ahead and integrate. Doing this, what do we get? On the left-hand side, we get natural log, or negative natural log, c epsilon minus q. And then on the right-hand side, I get 1 over rc times t, plus an arbitrary constant, which I'll call alpha, so as not to get confused with capacitance. So now, of course, our goal is simply to solve for q. So we'll bring over the negative side and then exponentiate. So I'll bring over the negative sign right there. Notice that alpha is an arbitrary constant, so I'm not doing any algebraic manipulations with it. And we're left with c epsilon minus q is equal to e to the minus t over rc plus alpha. Again, because alpha is an arbitrary constant, I can rewrite this e to the minus t over rc times e to the alpha using my properties of exponents. But then I can choose to rewrite e to the alpha as a new arbitrary constant, which I'll just rename alpha as well. Okay, so c epsilon minus q is equal to alpha e to the minus t over rc. Therefore, q is equal to c epsilon minus alpha e to the minus t over rc. Our last step is now to determine the value of alpha. For that, we use our initial condition. And our initial condition is that q of 0 is equal to 0. Plugging in 0 for t, we get 0 equals c epsilon minus alpha, which tells us that alpha is equal to c epsilon. Plugging that in, then we get q of t is equal to c epsilon times 1 minus e to the minus t over rc. And as an important fact moving forward, rc is what we will call our time constant, tau, and regulates how quickly current decays or charge builds up in our circuit. One last point. At this point, we can also determine the current in our circuit simply by taking I is equal to dq by dt, which gives us I of t is equal to, we get a negative in our derivative, which cancels this negative. We have c epsilon over rc, e to the minus t over rc, which becomes epsilon over r, e to the minus t over rc. Indeed, at t equals 0, this just becomes epsilon over r, and as t goes to infinity, this decays down to 0.